So, just recollecting a little bit of what went in the previous lecture, it was on this slide. We had said that two-level system will not work for lasing action or to get the kind of stimulated emission that we want. We want the stimulated emission to amplify, okay? And that is the lasing action. So, in order to get lasing action, two-level system has to be discarded. So, what can be done? What we have to do is we have to bring in pumping. You can't let the system remain in an equilibrium state. Okay. Then you do not get population inversion. You at the most get N1 equal to N0, but we want N1 greater than N0. So, what do? We bring in a three-level system. So, a three-level system is shown here in this circular patch. So, you have E0 here, you have E1 here, and you have E2 here. So, you have three levels 1, 2 and 3. Okay. So, now you have an incident photon which has a frequency E2 minus E0. It has to have E2 minus E0 in order to elevate this particle onto this level. Okay. For the moment, let us assume that this level, we assume that it does not have much. Perhaps in an equilibrium state it may have a few things, but we assume this part is empty. Okay. So, you have elevated one particle to this level by giving a photon which is equivalent to this energy difference. Now, what do you do? Now, what you do is you just wait for some time and you let this particle come down on its own here. So, you could think of it as spontaneous. Spontaneously it comes down, but then there is no emission. So, it is a non-radiative transition. So, quite often in many systems such non-radiative transitions do take place. Okay. So, this particle would like to stay in this level E1 which is lower than E2, because you want to be at a lower level state. Okay. So, it just jumps down to this thing without radiating anything. Okay. It just falls down here. Now that the particle is in E1, it can come down to E0, okay, and it will radiate something. Okay. So, what we have done is we have used a photon which has an energy difference of this, but our lasing action, the stimulated emission that we want, our lasing action is here, is this energy level. So, you have stimulated it to some other energy level, and the stimulated emission that comes out, it is in this level. Okay. Now, the wavelength or the frequency of this emission is E1 minus E0 and not E2 minus E0. Okay. This is easy to understand. So, this is the stimulated emission. But why do I choose such a system, a three-level system? That is because I can stimulate with the incident photon. Basically, the word used is pumping. I pump up all these particles onto this level. Okay. So, I am using some external pump mode. It could be a photon, or it could be some discharge system, some way of giving energy, and it goes up here. Okay. And I will be able to take out, in principle, if all the particles that are here can go up here. Okay. Now, when these particles just fall down to this level, the population N1 here is more than the population N0. Suppose you have taken up more than half the population from here to here. Okay. And now, instead of this E1 and E0 here, which is here, we are considering the E1 and E0 in this system. So, all the population that has gone up here tumbles down to this level, and then by stimulated emission falls down to the ground level. So, you have achieved a population inversion. That means the population of N1 is much more than N0. It is not equal, it is much more. So, you are getting this lasing action here. So, this is called a 3-level system. Actually, in a 3-level system, you could even have lasing action here in this black line. Lasing, you could get stimulated emission here. So, you have pumped up all the particles here, but you have pumped up in such a way that all these particles from the ground level have reached this, and this level is relatively empty. So, you can achieve N2 greater than N1. The moment you achieve N2 greater than N1, you will get amplification, and that is what is the lasing action. So, you could have a transition from here to here which is radiative. Okay. It depends on the kind of the material in that system. Okay. We will come across more of that as we study the different types of lasers. Okay. We will know which medium is being used, and which medium can give a 3-level system easily, and which medium cannot give a 3-level system. So that's an important part, a selection of medium in order to get lasing action. Now, we can do one more thing. We can have a 4-level system here. So, 3-level is fine, it will work, okay, not that. But quite often it may not work at some time. It may be a critical action, and then the pumping required might be much more. It may be difficult to pump up to this level, okay. Or the energy that is used in pumping, requirement of that may be much more. Then a 3-level system won't work. So, then we go to a 4-level system. So, you have N0, which is a population of E0, and you have E1, which is the population of N1, E2, which has a population of N2, number density, and E3, N3, which has a population of N3. So, obviously, the maximum population is N0, the next in equilibrium, next population is N1, next little more rarefied population is on E2, and the rarest population is on E3. So, now what we've got to do is we've got to pump up all these particles onto this level. Okay. So, in ideal case, you think you have pumped up some of these particles here, not all of them, probably you cannot pump up all of them, and you may have done it with a photon, say E1 minus E3, which is the difference between this and this. Okay. So, these two you would have done. So, you are pumping it by nu, which is E1 minus E3 here. Now, what happens to all the population, all the particles that have gone down? In a non-radiative transition, it can just tumble down to E2. By non-radiative transition, I mean when from this top energy level, it tumbles down to a lower energy level, no photon is given out. But then where does that energy go? That energy is sometimes transferred to other atoms or other molecules which can get excited, and in a sense physically what you see is the temperature of the system may go up. So, you are just increasing it, the system becomes hot. Once it tumbles down to E2, actually the population of E1 is as good as 0, very little population. You have pumped it all up to the 4th level and then it tumbles down to the 3rd level. So, obviously, you have a population much more in E2 than in E1. Okay. So, you have got population, your N2 is greater than N1. You have got population inversion in these two levels, and lasing action can take place here. So, you have got this stimulated emission here, and this radiation will grow and grow exponentially. That means amplification is taking place. That means lasing action is taking place. Okay. So, that is the advantage of a 4-level system. And how is it better than the 3-level system? It is better because the energy that you put into pumping may not be as much as in a 3-level system. Okay. So, so this is the 4-level system. So, in practical cases you do have a 3-level system and 4-level system, but not 2-level system. So, let us see what more conditions are required. This is not enough to get lasing action. Some more conditions are required in order to get lasing action. Okay. So, what is that parameter that we require? It is an optical resonator. What do I mean by an optical resonator? Suppose you have a medium, you have stimulated emission, you have these photons, stimulated emission photons, which are amplifying in this active medium. Active means you are getting stimulated emission there, that is why it is called an active medium. So, it starts say from one end on the right and it keeps getting amplified as you are going, start from the left and it is getting amplified as we go to the right. So, since this is getting amplified, you will need a medium which goes on and on forever. That is not possible. So, what has been devised is you put 2 mirrors here, mirror 1 and this is mirror 2. R1 and R2 are its reflectivities. So, you have one photon which starts from here, it keeps getting amplified, it goes and goes and goes. It goes and gets reflected from this mirror 2 and goes back into the medium. So, it goes back into the medium and it gets amplified. It goes to this mirror, gets reflected again and just goes on. So, it bounces back and forth between these mirrors. So, that is what is called an optical resonator. So, it is a clever way of going into amplification of this stimulated emission to get lasing action by placing 2 mirrors with the active medium in between. Okay. It sounds very good as a principle. This is called a oscillator, optical oscillator. Now, let us see what are the conditions which you have to apply to an optical resonator in order to get lasing action. If alpha is the gain coefficient and gamma is the attenuation coefficient. Alpha is the gain coefficient means it is the same as in the previous slide, alpha n1 minus n2. Okay, so, that is the gain n1 minus n2 and the constants which are attached to it. Now, gamma is a new term that I have introduced in this slide. It is the attenuation coefficient. Why do I need an attenuation coefficient? Because as the photons are travelling up and down here, there are lots of losses. Maybe some photon by chance it hits not the mirrors, but it hits in some other direction. So, there is a loss there and there is some absorption losses. And so, we are considering all the, so that is what attenuates your beam. Here we are not considering, when I say gamma, we are not considering the attenuation because of the reflection. We assume that the reflectivity is 100% of both the mirrors, but again that is an ideal case. You will always get a reflectivity R1 and R2, we will call it R1 and R2 of mirrors M1 and M2. They may be 99.9% or 99%, but in practical cases it is never 100. So, gamma is the attenuation which does not include R1 and R2. It is just the other losses as the photon is travelling in the medium. Now, the active medium, the active medium amplifies by e to the power alpha d, that we have seen before. We had called it S is equal to S0 e to the power alpha z. In place of z, I am saying d, because d is this total length of this active medium or between the 2 mirrors. Okay. The active medium amplifies by this e to the power alpha d, but at the same time there are certain losses as it is travelling up and down. and the losses will be e to the power minus gamma d, minus because it is a loss. Just at M2, that means here, the intensity is I. Suppose the intensity is I here at this point. Intensity you can relate it to the flux basically. You know, as the flux increases, your intensity also increases. Just the units will be different, but the entity is almost similar. So, I will call it I at this moment. Intensity I is modified to, so I have started with this intensity here at this point, okay, is modified to I e to the power alpha d, okay, and into e to the power minus gamma d. That means I have started with intensity I, but because of the amplification I have to multiply it by this, and because of the losses again I have to multiply by e to the power minus gamma d. So, that becomes I e to the power alpha minus gamma d. After reflection of R2, suppose it start here, after reflection of R2 of M2, mirror M2, the intensity is modified to I R2 e to the power alpha minus gamma d. We have just multiplied by a factor R2, which is the reflectivity of mirror R2. After passage through the active medium and the distance d, the intensity is modified again. Okay. The intensity is modified again. So, you have to multiply again by e to the power alpha minus gamma d. Okay, here alpha minus gamma d. So, it has been modified as it goes from here to here. So, I R2 e to the power twice alpha minus gamma d, 2 comes because here you are multiplying it. After reflecting of M1, we have to introduce the factor R1 because of the reflectivity of this. This is one round trip. For laser oscillations to begin, it is obvious that R1 R2 e to the power 2 alpha minus gamma d should be greater than 1. So, what we have done is one round trip. One round trip is you just follow this red line. You start off from here, you are getting amplified, amplified, amplified. You go to R2 and then again you are amplifying, amplifying, amplifying in the medium, and then you reflect off R1 and come to this point. So, this is one round trip in the medium. So, in this round trip there have been some losses and there have been some gain, okay, and that is encapsulated into this formula. Okay. Now, these losses and gain, if you put them together, if it is greater than 1, it is gain. Okay. So, what you need from an optical resonator is the condition R1 R2 e to the power 2 into alpha minus gamma d is greater than 1. So, if you do some just jugglery, you can find alpha is greater than gamma minus 1 upon 2 d ln R1 R2. So, your gain has to be more than your losses. So, that is what we have to try out. Okay. In these are the gains that you have to, the gain has to be more than the losses. Okay. So, that is what we have to ensure now. So, you have all these conditions as I have gone through. There is one more condition, that is the line broadening. I will be talking about the line broadening in the following slides, where I will discuss that the emission or the lasing action is not one exact identical line, you know. Then it would be a delta function, okay. But it is not a delta function. Okay. If it is not a delta function, that means that frequency has been broadened. And does this active medium support all those frequencies? If it does, then you will get lasing action. If it does not, then no lasing action. So, that is what we will be concentrating on, the line broadening effects.